We're moving out of mechanics into fluids and thermal and waves. Something new, something different. So let's take a look at our schedule really quick. So today, homework 11, next Monday homework. So we're going to try to cover 11 and 12 this week. Try to be done with. We'll try to get all the way through 11 today, chapter 11 today, and then cover chapter 12 Wednesday. Let's think about them. Let's actually okay, so we might change the order this week a little bit. Go Monday and Tuesday, learning chapters 11 and 12, and then Wednesday do 11. How does that sound? Is that okay with everybody? Because what we'll do is we'll do a lab. We'll do one lab for these two chapters. So we'll try to cover both chapters quickly and move on to the lab. And the homeworks aren't terribly difficult. And you'll see the subject's not really all that difficult either. It's kind of new stuff. But let's go ahead and get started. So you've dealt with liquid, solid, gas before, I'm sure. Gas, liquid, solid, whatever you want to say. It's all liquid gas. 3 states of matter, right? There are actually more states of matter than this, but these are the ones we're going to deal with for now. And one of the ways that we represent these 3 is to show that solids often have a very organized structure. And the reason it's organized is because of bonding that occurs between the particles that make up the material, right? And here they're showing this kind of square structure. It's not usually square. Sometimes some materials are more organized than others, but usually it's not square. But the point is that there are these particles the materials are made of, and sometimes they're considered atoms, like in gold, pure gold. It's just atoms that are the particles making up the material. But in other materials like this countertop, which is an amorphous material made of lots of different things together, then it's just a mixture of different molecules, really. It's a lot of different molecules that are bonded together in different shapes and formats. But the result is that these things become very, very difficult to like penetrate or break or whatever else. Not necessarily difficult, but more difficult than, say, a fluid or a liquid, because of the bonds. Essentially, these bonds are electrostatic in nature, and the bonds in your hands are electrostatic in nature, so it feels solid, right? Oftentimes, not always, but oftentimes these things are very dense compared to liquids and gases, because these bonds are often holding these particles very close together. That means you have more mass in a smaller space. So they are heavier for us. You have a small solid is often heavier than a small piece of liquid. Not always, but often. And that is again due to this bonding, holding these masses very, very close together and packing a lot of matter into a small space. Liquids have a little bit of bonding going on, but it's not very organized bonding, and it's not very strong bonding. The bonds are temporary bonds that just kind of they kind of get close to each other and attract each other and hold on to each other, and then they separate and go attract something else, right? So this would be represented by these particles that have these kind of affected trajectories. In other words, their movement is affected by how close or far they are away from other particles in the liquid. And that's why liquid is kind of wet and sticky, is because it does have this bonding going on. And some liquids are wetter or stickier than others. You know, it's very easy to get wet with water, for example. Water will really make you wet because it has a very strong kind of bond in between the molecules and the molecules with other things like your skin, your hair, whatever else. But there are some liquids that don't stay on you at all. If you pour gasoline on your hand, for example, gasoline does not make you wet. It just doesn't. It kind of pours on you and then evaporates and goes away. The bonds on gasoline are very, very, very weak bonds, and they're easily broken. And it easily kind of escapes from itself. Oxygen, or not oxygen, but gases in general. Oxygen being one type of gas. There's also nitrogen, helium, carbon tetrafluoride, and other gases. But anyway, all kinds of gases out there in the world, and gases have hardly any bonding at all between the molecules or the atoms or whatever it is that is making up the gas, the particles of the gas. There's hardly any bonds at all, and they almost never encounter each other. They don't interact with each other hardly at all. So gases are just free particles that just kind of fly around and do their own thing. And you can have something, of course, you can have oxygen that you can turn into a liquid. Oxygen can be a gas, but if you compress it down into a tight enough space, it will actually form a liquid. You get liquid oxygen. It turns out to be quite a cold liquid at normal pressures. And you can even get solid oxygen. Solid oxygen can be cooled and compressed till it's like a chunk of ice, right? And I will be purchasing some dry ice here for another experiment later, and we'll play around with the idea of having a gas in a solid form. But you know, even air you can compress down. Air is mostly nitrogen. You can compress it down until it becomes liquid nitrogen. Liquid nitrogen being a very cold liquid, and you can cool that down and freeze it into a solid, right? So the three states of matter, and all that entails. We're going to start off by talking about density, the definition of density. Density is, we use this Greek letter, it's rho. It looks like a P, but it's a rho. It's actually the Greek letter for R instead of the Greek letter for P. So this is called rho, R-H-O, if you're trying to type it into my open math, R-H-O. And density is defined as the mass of an object divided by the volume of an object. Okay? And essentially what density means is how much mass is packed into a space, small or big, doesn't matter. But how much mass is actually packed into a space is the definition of density. So here are some densities of particular materials that are pure material. There's no air gaps in them. As soon as you fill a material with an air gap, it changes its density, or you fill it with a liquid gap or another gap. Like you can take a block of wood and hollow it out and fill it with lead, and you'll increase the density because you've filled in a space of the wood with something that has far more mass. Or you can hollow out wood and leave it empty. Leave it out, and then you've decreased the density because you've removed something that is heavier than air, and the air replaced it, right? But if it's just a pure material, like aluminum, if it's pure aluminum, it has a density in its solid form at 2.7. Up here it says kilograms per meter cubed or grams per millimeter. So those are the units, it's mass per volume. So 2.7 kilograms per meter cubed. 10. It's 2.7 times 10 to the 3 kilograms per meter cubed. So if we had a meter cubed is about the area underneath your tables there. So if you take the area underneath the tables, it's a little bit less than that, and filled it up with solid aluminum, it would be about 2.7 thousand or 2,700 kilograms of aluminum. Compare that with brass, which is 8.44. It's almost 3 times more dense than aluminum. Copper, about the same, since brass is mostly copper. Gold is a lot more than that, right? 19. Gold is quite dense. And iron, about the same as brass, a little bit less than brass. Lead, about 11.3, right? Tungsten, about the same as gold. Uranium, about the same as gold. Concrete's about the same as aluminum. Cork, 0.24. Cork is a naturally occurring substance that comes from a tree, and it's very, very porous and filled with air. Right? Common glass, 2.6, is about the same as aluminum, 2.7. Granite, you know what El Capitan is made out of? About 2.7, about the same as aluminum. Earth's crust, about 3.3 on average, a little bit more. Wood is about 0.3 to 0.9. Ice is about 0.9. And bone is 1.7 to about 2. Now, on this scale, anything that is over 1 is going to sink in water, and anything that is under 1 is going to float in water. Water having a density of 1 times 10 to the 3 kilograms per meter cubed. Now, the reason that water is at 1.000 is because the metric system of kilograms and meters and everything is based on density of water. This is because when they were first trying to figure out a good system for measuring things, they said, well, water is really important to biology, and water is really important to chemistry. And so water must be really important to science, so we're going to make everything based on water. And that was in 1700 something. It's a ridiculous notion looking back on it now. It makes no sense at all to scientists now, because water is just a molecule. It's just, something that, sure, it's necessary for life. Sure, a lot of chemistry happens with water, but to a physicist, water is not fundamental at all. So we still use this system, of course, but the more fundamental you get into physics, the less you use it. But anyway, that's all right. So water at 4 degrees Celsius is 1,000 kilograms per meter cubed. So anything less than that will float. Anything more than that will not. Excuse me. So you can see here why ice floats. Ice is the word for solid water, right? Solid water actually has less density, is less dense. In other words, it has fewer molecules packed into it, into a single space, a particular given space, than liquid water does. So when you put ice cubes in liquid water, they float. That's not true of carbon dioxide. If you freeze carbon dioxide, you get dry ice. If you put dry ice in liquid carbon dioxide, they will not float. They will sink. Blood, 1.05, it will sink in water. Seawater, 1.025. Mercury. Mercury is a liquid metal. So mercury is a naturally occurring substance. It's on the periodic table. And it's a heavy metal. It's considered a heavy metal. Heavy metals are metals that are quite dense and usually quite poisonous. I think I have some, but I can't remember where I put it. Have you guys ever seen mercury before? Have you seen liquid metal? I have some in the back room somewhere. I have to go dig for it. Maybe I'll try to find it. But anyway, it is poisonous, and this is why they say that you want to have mercury-free paint or mercury-free this, mercury-free that. It's similar to having lead-free things. The funny thing is that people were so fascinated with mercury when they discovered it that they thought it was magical substance. So when they got sick, they would drink mercury. They'd take a tablespoon of mercury. Not so good for your body, actually. But they did a lot of dumb things before they understood things. Here's alcohol. So alcohol is 0.79. Alcohol is less dense than water. Will float. So will gasoline. Will float. And glycerin. Glycerin is the major ingredient in liquid soap. So shampoos and liquid hand soap and things like that. Glycerin is dish soap, and it will sink. Try that with your dish soap at home. It sinks in water. Olive oil floats. So does engine oil and lots of other oils. Most oils are less dense than air, or less dense than water. But look at the density of air. So these are the gases. Air has a density of 1.29 times 10 to the minus 3. So in other words, it's 1.29 kilograms per meter cubed. So all the air under the table under there has a mass of about 1 kilogram. Can you believe it? It's true, air does have mass. If you fill your tires on your car with air, you will actually make your car heavier. Your car is heavier when you fill your tires because of the air that you compress and put into those tires. Carbon dioxide, almost double that. Carbon monoxide, also about the same as air. So air is about the same as nitrogen. So here's nitrogen, 1.25. Air is 1.29 because it's mostly nitrogen. It has a little bit of carbon dioxide in it and some other things in it. It has oxygen in it. Here's oxygen, which is much more oxygen than it has carbon dioxide. In the media, or the people that are always talking about global warming, they want you to believe that carbon dioxide is this huge thing in the atmosphere. It's less than 0.5% of the atmosphere, and it really has not grown much. It's 400 parts per million, and it's been near 400 parts per million for over 250 years. Goes up and down. It's not changed much, even in the past 100 years. It hasn't changed that much. And they want you to think that the temperature has changed too on the Earth, and the temperature has changed about 0.5 degree up and down for the past 200 years, as long as we've measured it. But, you know, they say those things to get money for their research. So when I was a kid, global warming wasn't the thing everybody was talking about. It was nuclear bombs. It was the nuclear proliferation. They were talking about all the dangers of nuclear bombs. And, you know, any bomb is dangerous, but really nuclear bombs are not really any more dangerous than other bombs. Other normal bombs have actually done far more damage than nuclear bombs, and way more people have cancer from going into coal mines than getting nuclear bombs or any kind of nuclear radiation. We've had, I don't know, 100 million people die of cancer from coal mining. 100 million probably over the last 100 years. And maybe 200 people have died from nuclear caused, you know, from cancer caused by nuclear radiation of some kind in the past 100 years. So it's kind of crazy. But it's all about politics and getting money for your research. So, but all these gases have these very, very, very low densities, 10 to the minus 3, 10 to the minus 3. And that's pretty common. For gases to have a very low density, there's just not a lot of mass in gas. It's just spread out. It's free to roam, right? So it's very, very low density. And there is actually a material, a solid material that has a density that is very, very low. I used to have some of this, and I'm kind of angry that I gave it away to somebody who said they were going to use it, and then they never used it, and so I'm kind of upset about that. But the least dense solid is a thing called aerogel. Let's get some images of it up here. So this aerogel here here's a great example of it. You have this brick right here. This is like a chimney brick. So this probably weighs about, I don't know, 5 pounds or something like that, 2 or 3 kilograms. And then you have this block of plastic underneath it. This block of plastic is so low in density that it probably weighs less than this piece of paper right here. Probably less than a Post-it note is its weight. Very, very low weight. But it's very, very strong for its low density. Here you can see this big block. This is a piece of aerogel, and it's sitting on top of these bubbles, just soap bubbles. That's how lightweight it is. And this stuff was invented actually again in my hometown I don't mean to be like bragging about my hometown all the time, but my hometown does a lot of inventing because they have these two national laboratories in it where they just do a lot of stuff. Here's another great one. They've made this aerogel now out of graphene, which is essentially pencil lead. So they've essentially what they do is they heat this stuff up and they infuse it with bubbles. They put bubbles through it while they're heating it up, and then as they cool it, the bubbles stay in the material and create this really lightweight gel. That's an oversimplification, but you can see this big block of this stuff. It doesn't even hurt this tiny little flower. You know, it's kind of impressive. It's just sitting on it. And I wish I still had mine because these demonstrations are cool. They're fun. Another property of these things is they don't transfer heat very well. So you put this flower on top and then you put a flame underneath, and the heat doesn't affect the flower, which is nice. Very interesting, right? But they invented this stuff, and then they found all kinds of interesting uses for it. This is very classic physics. Physicists have this tendency to invent things that they don't know what they're going to use them for. They just invent them because they can. We can invent that. We can figure that out. Let's make that work. Let's make it happen. The perfect example of that is the laser. Here's another great example of graphene, a graphene aerogel on top of a dandelion. It doesn't even bother the dandelion. Kind of cool. So, but the laser was invented actually not at mine in my hometown. It was invented at Bell Laboratories, which is a commercial laboratory made by the Bell company, like the old phone company. And that laboratory, they invented what is called the maser, which was a microwave laser. It didn't use visible light, it used microwave light. But they had no idea what they were going to use it for. They didn't know, they just wanted to do it because they knew they could. So they just kept working on it and eventually invented the laser. And of course, lasers are used everywhere now. You can't hardly walk down the street without using a laser in some form or another. But the samples that I had of aerogel, the lightest sample or the least dense sample was so non-dense that you could only open in a room where there were no air ducts, because if there were air ducts, it would blow out of the box. And it was so non-dense that you couldn't see it unless you looked at it sideways, and so you had to open the box above your nose so that you didn't breathe on it. Because if you breathed on it, it would go flying out of the box and you'd never find it. And then you had to look at it from an angle, and it was best to use an ultraviolet light, because an ultraviolet light would make it kind of glow, and then you could see it in there, and it was super delicate. It was kind of broken into pieces, and it was about 3 times the density of air. It was only 3 times as dense as air. So if you actually let one go in the air, it would actually float around this chunk of solid material. It kind of float around in the room. You could never find it again because it was difficult to see. And you can see how difficult it is to see in some of these situations. It's difficult to see, but that's a cube. But you're looking right through the corners. The corners are invisible. You're just looking right through them. You can kind of see their shadow on this guy's shirt behind it. But besides that, you can't really see the actual corners. The light just goes right through them. Very, very low density solid material. And they found tons of uses for this. They've used it to collect particles in space. They use it for electronics. Use it for heat dissipating materials and things like this. All kinds of great things. In fact, the tiles on the space shuttle use this type of material to protect the space shuttle from being from overheating and things like that. But so very, very low density. And then the highest density, I think, oh, here we go, the highest density solid, osmium, yeah. So osmium in the periodic table, it looks like, this is what it looks like in its solid form. It has this strange crystalline form. And it is the highest density. I don't know what the density actually is. So osmium is 22 grams per cubic centimeter, so it's 22 kilograms per 22,000 kilograms per cubic meter. So if we had a block of osmium under your table, it would be quite heavy. 22,000 kilograms. Lots and lots of bits. That's, uranium comes in at 20. So anyway, that's density for you. And this is often confused with things like weight. We say something's very light if it has a low density. Well, it's not necessarily. Hey, feathers have a low density. Here's a ton of feathers. And bricks have a high density. If you have a ton of bricks and a ton of feathers, they weigh the same. Right? That old joke. Which weighs more, a ton of bricks or a ton of feathers? They weigh the same. Right? It's just that bricks take up less space. So how do we calculate, how do we use this in calculating things? We can use this equation to calculate how much mass of water there is in a reservoir. If we figure that the surface area is 50 kilometers squares and have an average depth of 40 meters, then you take the surface area times the depth, and that will give you the volume of the reservoir for V. And then the density of water is 1,000 kilograms per cubic meter, right? So you would plug that on this side and solve for the mass. And so you calculate the volume, solve for the mass, you get 2 times 10 to the 12th kilograms of water. This is the Three Gorges Dam in China, and it's just not all that impressive in my opinion. My favorite dam is the Hoover Dam because it was the dam we visited on our family vacation when I was a kid. When I was a kid, this is what it looked like. There was a road going across the dam. This is Lake Mead, which is near Las Vegas. It's a big party lake. People like to go party around a big old lake with lots of canyons and stuff. Hoover Dam is super tall. I want to say 300 something feet. And when it's releasing water at the base, this is what it looks like. It has all these water jets coming out when it's releasing its water down at the bottom. It's always releasing water, but that's when it's releasing water at a max, kind of at a maximum level. Looking down the dam, that's pretty cool. Now they have this bridge going across so that the road down here is not really for access for anybody. You can't just cross the bridge this way on the road anymore. You used to be able to, and you used to be able to stop in the middle and take a look. But now the highway goes across this bridge instead because they're afraid of somebody planting a car bomb up here and flooding Arizona or something like this. But that's an impressive dam. And if you ever go there, you can take the dam tour. We did that. We took the dam tour with the dam tour guide. Went to the dam tourist shop. It was fun. We even got a ticket from the damn police. That's Hoover Dam. Look at that flag. That's humongous. Built in the time of J. Edgar Hoover, back in the 30s, 20s, back in the 20s. Wow, look at that. That's the construction of it, I guess. That's what it looked like before. Very cool. Anyway, so I think that's a more interesting deal. Okay, so pressure. Now, what is pressure? We're learning about pressure. Pressure is when you apply a force. Now, all the forces that we've dealt with so far, we've assumed happen where that arrow points at the object, right? But that's not real. In real life, if I come up and push you, there's pressure, there's force that is distributed all the way across my hand. So if I go and push you, my finger pushes you, and my knuckle pushes you, and this knuckle pushes you, and this knuckle pushes you, and this hand pushes you, and this part of my hand pushes, and my ring pushes you, and everything, every part pushes. So there's like force vectors coming out everywhere. Instead of representing it with like a gazillion little arrows coming out, we just say that there's a force that is distributed over an area. Now, it could be an even distribution or it could be an uneven distribution. For the purposes of this class, we do even distributions to make it easy, and we just say that the pressure is equal to the force over the area. So we have some amount of force that we push with, and then if I'm pushing with one hand, then that's the area of this hand. If I'm pushing with two hands, it's 2 times the area of my hand, right? And that's the area, and that would give you amount of pressure. Now this accounts for things like don't walk on the basketball floor with high-heeled shoes or cowboy boots. Why? Well, if you have a weight, let's say you have a weight of 500 newtons, it's 1,000 newtons, make it easy. So if your weight is 1,000 newtons, in other words, that's the amount of force you push down on the floor with. And then you have your foot. So my foot, if I put my 2 feet together, they have a surface area of about 1 foot square-ish or so. So that's about 1/9 of a cubic meter. Let's say it's about 1/10 of a cubic meter. So I would take the force, which is 1,000 newtons, divided by the 1/10 of not a cubic meter, a square meter, 1/10 of a square meter, which would be the area that my weight is acting on. So it's 1,000 divided by 1/10. When you divide by 1/10, it's like multiplying by 10. So the amount of pressure under my feet is at about 10,000 newtons. That's a lot of pressure. But what happens if your high heel is like that? Like a square centimeter, right? A square centimeter is 1/10,000th of a square meter. So you take that 1,000 newtons, and when you're stepping on that high heel across the floor, you divide that 1,000 newtons by 1/10,000th, and that's when you divide by 1/10,000th, it's like multiplying by 10,000. So you take 1,000, you multiply by 10,000, you get 100,000 newtons. 10 times more pressure at that one point, right? And then you get little divot marks in your floor. Right? You ever looked at a basketball floor and seen those little? That's high heels, and cowboy boots do the same thing. Because when you walk in cowboy boots, you're putting that sharp heel on the floor and then rolling your foot forward. Whereas other shoes don't have that sharp corner, right? So that's why they say they don't like dress shoes for the same reason. Anytime you have a sharp corner and that sharp corner goes down first, and a lot of new boots and high heels and dress shoes now on that back part of that heel have a rubber pad. And what that rubber pad does is it spreads out and it applies that force over a bigger area so that it's not putting dents in the floor quite so easily. And this is actually how you get a shot. I gave myself a shot on Friday. I have to give myself a shot every 8 weeks for a condition I have. It's kind of fun. I never realized how much fun it would be to give myself a shot. Especially if somebody's around and when you give yourself a shot. Like they're like, ew, and they get all squeamish. It's kind of fun. But anyway, the reason that things can cut into your skin, a knife or a needle or something like that, it's people are afraid of sharp objects for cutting, so it's not the sharpness, it's the smallness, which you could say is the same thing. But really what is happening is when you have a very, very small object, the smaller you can make it and you apply just a little bit of force to your skin, the pressure at that very, very tiny area, that's that very, very tiny blade or needle, the pressure gets really, really high because the area is super, super tiny. You don't even have to apply much force. With my needle, it's hardly any. With the needle, I just have to push a little bit and it goes in 2 inches, 3 inches, just right in. Not a problem. I don't even feel it. Takes very little. But the same amount of pressure if I use my finger or even like a pencil or a pen. I shove a pencil or a pen into my stomach or my arm, it just makes a dent, just pushes my skin. It might hurt a little bit, but it's the same amount of force, but the pressure is so much less because the area is so much bigger. Right? So now pressure is force divided by area, which is going to be newtons divided by meters squared, newtons per meter squared. But we give it a name. It is named after a guy named Pascal. So the unit, 1 Newton per meter squared, is 1 Pascal. But the confusing thing about pressure is that we've been using a lot of different units for pressure over the years. And so when we're measuring atmospheric pressure, then we use something called millibars sometimes, or atmospheres even. So bars are a unit of Pascal that's equal to 1 times 10 to the 4th Pascals, or 10,000 Pascals. We also use pounds per square inch. You've heard that one before. PSI is a pressure, right? Pounds per square inch. That's force per area. Why is there atmospheric pressure? Why is there pressure around us? So there's one Newton per meter squared is 1 Pascal, and there's 100,000 pascals of pressure on your skin all the time from the air around us. Why is there? Why is there pressure? Why does the atmosphere have pressure in it? It's force per unit area. What force is there in the atmosphere? What keeps the atmosphere on the earth? What keeps us on the earth? Gravity. So there's this air around the earth, and it stays there because of gravity. If gravity didn't exist, we wouldn't have any atmosphere. We wouldn't even have a planet. But the gravity keeps the atmosphere on the earth. And it's pulling the atmosphere towards the surface of the earth. So that's a force. And there's a surface on the earth. That's an area. It's force per unit area. Right? And so you could think of it like this. You could think of it like when you're walking around outside, you're walking under a tall column of air that's pressing down on your head and your shoulders. And the air that's pressing down outside of your body's top here is pressing down on the air that's around you, and that air around you is pressing in on the sides, right? Without that, your body wouldn't work right. When the pressure is released from around our bodies, the liquid in our body tries to get out. So we have a lot of liquid in our body, blood and water and stuff like this. That liquid stays a liquid because of the pressure pressing on it. If the pressure doesn't press on that liquid, it will boil and actually try to get out as a gas. And this is one of the things in science fiction that is debated all the time. What would happen to a human body if they were exposed to space immediately, like suddenly? So in science fiction, they do that all the time. Somebody gets thrown out of a spaceship. Well, what would happen? Well, of course, it's very cold in space, so things would start to get cold very quickly. But before that happened, the pressure would go to zero immediately. And what would happen is that your blood would start to boil, and all the liquids in your body would start to boil and turn into gases. And they would try to escape your body. And as they tried to escape your body, as they boiled, they would expand into gases. And in trying to escape your body, you would burst a bunch of blood vessels all over your skin and your eyes. And you would essentially be bleeding all over your body. And it'd be kind of gross. And then as that happened, things would get very cold very fast, so you would freeze at the same time. So you would boil and then freeze simultaneously. It wouldn't be pleasant. This actually happens to people who climb Mount Everest, actually. Because when you get up into the high reaches of the atmosphere, the pressure goes way down. And the blood does not, the blood in the body does not, the blood vessels in the body can't contain your fluids anymore very well. And it's called edema. You get bleeding in the lungs, you get bleeding in the eyes, you get bleeding in the ears, bleeding in the sinuses. Some people can tolerate it better than others. People who have lived in the Himalayas all their lives, for example, the Sherpa people, they they can't even live. They can't live below 15,000 feet. If you bring a Sherpa from who's the Sherpas live mostly in Nepal, and if you bring a Sherpa from their mountain homes up above 15,000 feet down to like where we live, they actually have the opposite problem with their blood. Their blood vessels are designed for up in those regions, and they can't live down here very well. So it's no small coincidence that more Sherpas have climbed Mount Everest than any other person. Every time somebody goes up there, they take Sherpas with them to as essentially to help them carry their gear and to carry them off the mountain in case they start dying. They call it the death zone up above 20,000 feet, 22,000 feet. Above 22,000 feet, most human beings just start to die, slowly start to die, and they can only spend a little bit of time up there, so they have to hurry up and get to the top of the mountain, hurry up and get down. And if they start to die a little too much, they bring a Sherpa with them to help them to get out alive. But still, I think the mortality rate's around 40%, 38%. If you go up above there, you have about 60% chance of living. Yeah. It's kind of crazy. I don't know if you've ever read anything about the Himalayas or anything, but there are literally dead bodies on the way up the mountain. So if you climb Everest, you're climbing past dead climbers who are in the snow, and they can't bring them down all the time because it takes a lot of effort. So they try to clean off the mountain every once in a while, but it's still just kind of a gruesome place, and that's all due to pressure, really. Pressure is the number one killer up there. It makes people sick when they can't get themselves off the mountain. Storms are another big killer up there, and falls, but the number one thing is people getting sick. Anyway, so this is pressure for it. Let's calculate a pressure. We have an astronaut at the International Space Station. Outside, the pressure is zero because there's no atmosphere out there. So if there's no gas or no liquid or no solid, there's nothing to do any forcing. The gravity can't pull anything against you, right? There's still gravity, but all it's doing is keeping you in orbit. It's not creating any pressure around you. So they have essentially a zero atmospheric pressure out there. And we want to know, we want to calculate so they have a pressure gauge on our tank, the air tank that's providing pressure inside the suit. What keeps her alive. Not only does it allow her to breathe, but it keeps her blood from boiling, right? So that's what they do. And they also have heaters inside their suits, or air conditioners, depending on if they're in the sun, they need an air conditioner. If they're in the shade, they need a heater. So, but anyway, the point is that they've got this 6.9 times 10 to the 6 pascals of force on the pressure on the pressure gauge inside the tank. We want to know what force that exerts on the flat end of the cylindrical tank with a 0.15 meter diameter for a 0.15 meter diameter disc on that tank. So what they've given us a diameter. To calculate an area, we'll need the radius. So we'll divide that by 2. That will be 0.075 meters. And then we square that, multiply by pi, and that will give us the area of that cylindrical tank right there. We've solved the equation for force. Pressure equals force over area. So force equals pressure times area. Then we plug in the pressure, and we get 1.22 times 10 to the 5th newtons. So 122,000 newtons of force on those air tanks. And have any of you lifted a scuba tank or anything like that holds air at high pressure? So they're heavy. I've got a couple in the back I should bring up. But they have to be. They have to be super strong to hold 100,000 newtons of force have 100,000 newtons of force on them. On Earth, these tanks have to be. If you're going diving, it doesn't matter if you have a heavy tank, because a heavy tank is actually a good thing. It helps you sink to the bottom, which is where you want to go when you're diving. But if you're like a fireman, a heavy tank is a bad thing because you have to climb over things, you have to move quickly. So firemen's tanks are much lighter, but they're very expensive to make them lighter. But a spaceman who's out walking in space, doesn't matter what their weight is, what the weight of their tank is. but it does matter to get it up there. So their tanks have to be super light as well. It wouldn't matter if they had a tank made of lead, really, once they got it up there. But getting it up there, everything that goes up there, it costs like, I think the estimated cost, it's like thousands of dollars per kilogram to get things into space. I don't remember the cost, but it's actually maybe even $1 million per kilogram or something like that. It's totally crazy cost. Here's a tire. This is what it looks like inside of a tire if you label the forces, right? So if you fill a tire with air, with more air than it would have just is sitting there, you start pumping it full of air, then you have all this force acting both on the inside of the tube and on the outside of the tube, like where the tread of the tire and where on the part where it connects to the rim. But also that goes up into the stem, and that's actually what holds the stem closed. This is why you can go up to a tire and push on that stem and let air out, because there's just a spring behind this. They usually put a spring behind it also, but for like a car tube. But you press that in, it lets air out, and if you have air pressure in there, it helps hold that air in, right? You ever wondered why on car tires that stem doesn't point straight up like this? Well, on bike tires it does, but on car tires it turns sideways. You ever wonder why? What would happen if you got going really, really, really fast? What happens to things like this? If you're going really, really fast, this thing is actually going to go outward towards the edge of the tire, right? And then I would let all your air out of your tires. So on a freeway, if your stem went straight up on your car, at a freeway you'd lose all the air in your tires. That's one of the reasons they put the spring in, because when they were first doing this, cars didn't go very fast on the highway, so the spring would just hold it closed. But now cars go much faster on the highway, they definitely have to turn them and make sure that the air doesn't escape from the tires. For bicycles, they created a new type of stem that is locked closed with a little screw on it, and because that was happening to cyclists racing. Once they got racing bikes up to about 30-40 miles an hour, they were losing all the pressure in their tires and going too fast, and more like 50 or 60 downhills. Here's another interesting thing. The swimmer is actually floating in the water, floating slightly under the surface. But down here at the lower levels of the water, there's more force because there's more pressure. The deeper you go underwater, there's more pressure because there's more water on top of you pushing down on you. So on the bottom of the swimmer, there's more pressure. On the top, there's less pressure just because of the difference in height. And that more pressure means more force, and that means the swimmer's going to float. Right? It's one of the reasons a swimmer would float. No, it's not the most important reason. So, how does pressure change as you go deeper into a fluid that's in gravity? So, if you're at the top of the Earth's atmosphere, there's hardly any pressure at all, almost zero. But the closer you get to the surface of the Earth, the more and more pressure there is because of all the atmosphere that's on top of you pressing down on you, right? It's like weighing down on you. And underneath, have any of you ever gone swimming and gone fairly deep, dived down to maybe 2 or 3 meters deep? And you can really feel that pressure on your ears, right? It's an extreme difference in air pressure under a liquid because a liquid has so much more density to it that the effect is more extreme, right? And it gets, to the point that it could get very painful. Down at about, I'd say 4 or 5 meters, it becomes extremely painful unless you learn to equalize your ears, essentially. Your ears are filled with a liquid, and that liquid can be put at different, your body can set different pressures in that liquid. And the way that you equalize that, there are different methods for it. One of them is to hold your nose, kind of pretend like you're blowing out without letting any air out. You can do it without holding your nose once you get at it. Kind of like a yawning motion. that equalizes the pressure. And essentially what your body is doing is it's changing the pressure inside your eardrums. The liquid, it's either putting more liquid in or taking liquid out, essentially. Or it's squeezing the liquid more, is actually more likely. More like it's going on. So it's squeezing it more and increasing the pressure. When there's too much pressure on your ears, your eardrums are getting pushed into your head. And that hurts because it's stretching something that has a nerve attached to it. And it can hurt so bad that it can break them. Now, going underwater, it takes quite a bit of depth. I think, I want to say 10 meters before you can do any real damage to your ears. But 10 meters is a long way. Most people have never gone that far. I think I've probably been that far twice in my life. Maybe 3 times. But very few people will ever go that deep in water to have any problems with their ears. But on airplanes, you definitely can feel the pain as you're going up and down. If you never equalize your ears, you'll start to get headaches, right, from that pressure difference in your sinuses and in your eardrums. And you can definitely feel the pain in your ears, and that's air pressure again. But that's lowering the air pressure. So as you're going up in the plane, you have less air pressure out here, so your eardrums are actually sticking out too much. It's like there's not enough pressure to hold them in. So it's the opposite effect. The liquid in your ears is pushing the ear out. And then you have to equalize to allow it to relax and not do that anymore. All right, so pressure varies with depth in a liquid or a fluid. It can be, so a fluid can be liquid or gas, really. So it's by the weight of the fluid above the area that it's on. And the mass, so if we solve the density equation for the mass, we get mass equals density times volume. And volume is equal to the area times the height. And the mass then is going to equal the density times the area times the height. And then we plug all that in for the mass into the original equation up here, and we get this equation, pressure equals density times area times height times gravity over area. And it turns out the area doesn't even matter because the area cancels out here. So it turns out it's just the height of the liquid that matters, the height of fluid, times the density of the fluid times the gravitational constant, 9.8. So it doesn't even matter what the area is at all, it turns out. It just matters the height. So if you want to calculate the pressure at the bottom of this container here, you need to know the height. You need to know what is the density of the liquid. What is it made of? If it's made of if it's water that's in this thing, then it's the density of water. If it's mercury, then it's the density of mercury or whatever. Right? So here we're going to calculate the amount of the average pressure on a dam and the amount of the force that's exerted on a dam. How much force that a dam has to, how much dam force, right? So we calculate the mass of the water already. That's from the previous example, one of the first ones. And so we know the mass. The dam is 500 meters wide and 80 meters deep. And we're going to take that for our area in part of this problem. First of all, we're going to do the average pressure on the dam due to the water. So we're going to take the pressure is equal to height times pressure times density times gravity. Then we're going to take average height. So the average height has an average depth of 40 meters. So the average pressure is going to be 392 kilopascal when we plug in those numbers. Right? We have height times density times gravity. Density and gravity are fixed numbers. And then we have the 40 meters of height. So there's our average pressure. That average pressure we plug into the pressure equation to calculate the force with the area of the dam. And the area of the dam is the 40 times 80, or whatever it was, or 500 times 80 rather. 500 meters times 80. And then we get 1.57 times 10 to the 10 newtons. That's a lot of force. 10 to the 10 is a huge amount of force. But notice that the pressure is 392 kilopascal. That's actually less pressure than atmospheric pressure. Atmospheric pressure is 10 to the 5th Pascal. This is, actually that's about the same as, I guess this is about the same as atmospheric pressure, but not much more. It's maybe 4 times atmospheric pressure. In other words, if we went and drilled a hole in the dam the size of your finger, you could stick your finger in there and hold in the water, keep it from coming out. That's actually an old parable from like Sweden or something. There's this old story about a boy who walks by the dam above their village and sees water coming out of a little hole in the dam, so he sticks his finger in the dam and saves his time. But he has to stand there and wait. And I think in the original story he actually dies with his finger in the dam and saves his time. But anyway, it's an old story. Here they do the calculating the air pressure above our heads. So if you have 1 atmosphere of pressure, so this is another measure of pressure. 1 atmosphere equals 1.01 times 10 to the 5th newtons per meter squared, or 101 kilopascal. And so that is the average pressure at sea level on Earth, is about 1 atmosphere, or 1.01 times 10 to the 5th newtons per meter squared. Here in North Platte, we're at about 4,000, I want to say 4,000 feet. I don't know, actually. Let's find out. North Platte, Nebraska. I want to say 3,000 something. Oh, no, not quite. 2,800. So almost 3,000. Ogallala is at 3,000 something. So at North Platte, we don't have the average the average pressure here is going to be higher or lower. What do you think? Is it going to be a higher pressure or a lower pressure if you're above sea level, which is at 1 atmosphere, or 100 kilopascal? What causes atmospheric pressure? It's all that air above your head. Do we have more or less of it if we're higher above sea level? Less of it. So it's going to be less air above our heads, less force on our heads, less pressure. Let's see if we're right. Let's see. Pressure, average pressure. Let's see if it's telling me pressure. I don't know pressure. Not helping me. Oh, here we go. Forecast averages. Oh, here we go, barometer. So the barometer measures pressure. So here's another strange unit of measure, the barometer reading in inches. This is inches of mercury, 29.19 inches. We'll copy that. Actually, we'll just search Google. So 29.91 inches of mercury, which is mg. We'll convert that. We'll convert pressure to Pascal. It's 101,286. It's actually the same out to a certain number of decimal points. So we're not much lower than the average. I don't know exactly what the average is out beyond 101, but right now we're about the average pressure. We're just a little bit below the average for sea level. Let's see what the pressure is in my hometown, see how much, if it's higher or lower. Livermore is like 80 feet above sea level. So the pressure is 30 inches, so they're definitely higher. Definitely higher pressure. All right, so anyway. So average density, how dense is the air density? If we use this equation that has height, density, gravity, and pressure in it, and solve it for density, then we need to know the air pressure, the density, and the height. And we go ahead and do that and calculate the average pressure in the atmosphere of 8.59 times 10 to the minus 2 kilograms per meter cubed. So that's much lower than the density of air at the surface. That's because up at high altitudes, the air is much, much thinner. Has much, much less density, much fewer molecules per cubic meter. So the average density is quite a bit lower than the real density. It's about 200 grams per meter cubed lower. Anyway. Oh, they also. So now we're going to move on to some of the principles of fluid statics as we're studying. The first one is called Pascal's principle. So Pascal's principle is kind of like a law where it's something that has been observed to be true all the time. And in Pascal's principle, it kind of is like this. If you have an enclosed container with a fluid in it, it can be a gas or a liquid, and you apply a pressure to that container at some point, a force to that container, then you can increase the pressure of the fluid inside the container. But Pascal's principle says that pressure will transmit itself throughout the fluid into the entire container. So if I have a balloon that's filled with air, and that air is at a pressure of 1.2 pascal, 1.2 atmospheres, or 120,000 pascal, for example. And then I squeeze that balloon and increase the pressure inside the balloon. All of the air in the balloon will increase its pressure, not just where I'm squeezing. Okay. And this principle is taken advantage of in what we call hydraulics. So this is a very simple hydraulic system. We have a small tank here that has a small radius, and a bigger tank here with a bigger radius, and it's connected by a pipe in the middle. And then the tanks are filled with this fluid, a liquid of some kind. But on top of the fluid, we fit these kind of lids that fit down inside the tank, and they seal off the fluid so the fluid can't get out. And these are movable. You can press down on this one on the left, and the one on the right will go up. Or you can press down on the one on the right, and the one on the left will go up. Either way. This is a very simple hydraulic system. When I apply a force to this one on the left, it creates a pressure across this area, and that pressure is the pressure that that this fluid gets. This fluid is actually exerts or has this pressure in it. That pressure transmits, and all this liquid over here also has that pressure. And this pressure in the liquid over here will actually exert a force across this area, and the force will go up here. But notice that this force vector here is small and this force vector here is big. Why is that? Well, because of Pascal's principle. We use the whiteboard, but I have to remember to use the whiteboard here. So let's go back here. So here's my system. Big tank, little tank. This one has a small area on it. We'll call it little a. We'll call this one big A. Right? The pressure that I exert on this, so these things that are movable are called pistons. So if I exert a force over here, small force, small f, on this area, then the pressure that is created inside this fluid, pressure P, is equal to little force times little area. But this pressure exerts itself all the way over to this side, same pressure. So it's equal to the same pressure on the other side, and it's going to create a force upward here across this thing. A pressure across this is going to be equal to a force. But remember that the area here is big, right? I just did this wrong, sorry. I was checking, just realized, I was looking at the picture and realized before I even changed it that I'd done something wrong on my picture. Where's my thing? Wiper, oh yeah. Force, sorry. Pressure equals force divided by area, not force times area, right? So I did this wrong. This is force divided by area. I'm just going to rewrite that. Come on, erase, dumb thing. There we go. Erase, 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 erase. Come on, erase. Okay, so anyway, going back. So this pressure is equal to force, little force divided by area, which is what I was supposed to say, not times area. And this one has a huge area in it. But it's the same pressure, right? If we're going to get the same pressure, this pressure is equal to little force over little area, and this one is over big area, we're going to have a big force here. Because big force over big area can equal little force over little area. Right? So the force over here ends up being much bigger. If this area is equal to 4 times the little area, then this force is going to equal 4 times little force. If it's 10 times the area, it's going to have 10 times the force. Now, can you think of any situation where this might be useful? Where you have one thing that you put a little force on, and on the other side you get a big force out. Could this be useful anywhere? Absolutely. In fact, I wager that all 3 of you used it on your way here this morning or this afternoon, and I did too. What did you use that does this? What did you use that does this? Where you pushed on something with a kind of a small force and applied a big force and kept you from hitting the car in front of you. Your brakes. Your brakes are a very simple hydraulic system. Behind your brake pedal in your car is a little piston called the master piston. Okay? Just a tiny little piston. In fact, I think there's 2 of them. I think the front and back brakes usually have separate ones, but just because they want you to have, if one fails, then you're good. But anyway, the point being is that you have this little piston here, and then at the other end you have big pistons on the brakes themselves, on the brake pads that are on the wheels, right? Here. You put a pretty small force here, and it transmits a huge force to the brakes on your wheels. If you had to directly brake your car, if this didn't work like this, you would have to press so hard on your brakes, it would be ridiculous. You would never be able to stop your car if you're going more than 10 miles an hour. It would just burn you. It would just burn right through stoplight. You'd hit the next car in front of you all the time. That's how difficult it is to stop a car using your feet. It's just not happening. The Flintstones, not happening. But with this, you get a multiplication. I think in a car, it's something like, I think the master cylinder has an area of maybe a square centimeter, and then like a quarter of a square inch. That these things have several square inches at the at the slave cylinders. So you get a huge multiplication. It's maybe 40 or 100 times stronger. So that is hydraulics. We do use hydraulics for all kinds of things. There is a drawback, however, because when you push down on this small cylinder, you move very little fluid because this cylinder is very, very small cross-sectional area. So when it moves down, it doesn't move very much fluid. And so not very much fluid moves over here. And even less movement happens on this one because it's a much bigger cylinder. So if you have a 4 times bigger cylinder on this side, and this moves 1 centimeter, this will move 1/4 of the amount. So what that means is your car brakes have to be very, very close. The brake pads have to be very, very close to the discs in order for it to actually hit the disc in time. So balancing that is very, very touchy. This is why brake discs often rub on the brake pads if the brake pads and discs are out of alignment. They have self-aligning brake pads and discs for this reason. So you have to have a very, very balanced system on this side. If you go the other way, if you went and pushed on this end, you would only have to push this one a little bit, and this one would move a lot. But you wouldn't get much force out of this end. You'd have to push 4 times harder on this end to get less force on this end. And they use that all the time too. They use these things backwards all the time. That's the way they use hydraulics on things like front-end loaders and other things like that. So you get a lot of movement from a lot of force instead of a lot of force from a little bit of movement. And here they actually show a nice little diagram of this. They're not showing disc brakes here, they're showing drum brakes. I think my van has drum brakes in the back, but not in the front, disc brakes in the front. Most cars just have disc brakes nowadays. But here's your very, very small cylinder, here are your much bigger cylinders. The master and the slaves, as they call them. And here's the equation that they solve. The pressure equals the force over the area on the first, and that equals the force over the area on the second. So same pressure, that's Pascal's principle. Solve that equation for the force or the area or whatever. You can solve this equation for anything you don't know and plug in everything else you do know. But I do warn you that oftentimes they'll give you the diameter, and you need to remember that when you're calculating the area of a circle, you need to use the radius. So you need to take that diameter, divide by 2, and then and then square it and then multiply by 5 to get your area. Right? Don't forget that. It's a common mistake students don't catch. So now we move on to gauge pressure. Now gauge pressure is the pressure above or below atmospheric pressure. So when you're going to measure the pressure in your tires, for example, the pressure in your tires is so many psi above atmospheric pressure. So that's a gauge pressure because it's using a different 0 point than zero pressure. Zero pressure is what's out in space, where there's nothing pushing on you, there's no forces, and you're just kind of floating around out there. That's zero pressure. When they measure your blood pressure, they measure your blood pressure in millimeters of mercury, and they tell you you have a blood pressure of 118 over 76 or something like this, right? That 118 is the high end of your blood pressure, and the 76 is kind of the low end. There's kind of a beginning and an ending blood pressure with your blood. So if your blood pressure is really high, that means that blood is more likely, like if you get cut, it's going to come out more quickly. You're going to bleed more quickly. People who bleed a lot have a tendency to have fairly high blood pressure, right? Before it stops bleeding. And people with fairly low blood pressure have a tendency to bleed very little. So when they want to take blood, you ever seen them like they're looking at your veins? They have you make a fist, right? When they have you make a fist, what that does is it slows down your blood, And when it slows down your blood, it increases your blood pressure, and then makes it actually increases the volume or the cross-sectional area of your blood vessels. And then they can see or they can feel, oh, that's a nice blood vessel to get my needle into. What they don't want is somebody with low blood pressure, and then that vein that they're trying to get into is like not very big. Because if they go right through it, you know what happens? You get internal bleeding, you get a huge bruise. Anybody had a bruise from a shot or taking blood or giving blood or anything like that? Anyway, what happens is it bleeds inside your arm, and then you get a big bruise, and it can be sore, right? So you don't want that. So they have you make a fist. When you slow that fluid down, it slows down and it fills up that blood vessel, and it makes it big and fat, and then they can get the needle in it. That's also why they put a tourniquet on, like they put a little strap on your arm somewhere to slow that blood down and make a nice big vein for them to get into. Nice high blood pressure. And that's actually how the blood comes out. You ever seen you see the little bottles that they put on? So they put the needle in, and then they put the little bottle with the rubber stopper in there. You ever seen that? Well, that bottle that they put in actually has been evacuated, so it has no air in it. They've taken the air out. It's a little vacuum. So when they put that in there, there's low pressure inside the bottle and high pressure in your vein. So then the blood goes from high pressure to low pressure. Fluids have a tendency to flow from high pressure to low pressure because there's low force, nothing to stop them. Here's a very simple gauge for measuring pressure. What they do is they have this springy bellows thing here, and then they have this little port where air pressure can come in. As the air pressure comes in, it squeezes on the bellows. And as it squeezes on the bellows, there's a pivot on this little angle and this spring that they know the strength of the spring, and it tells you the pressure. So this is essentially when it's at 10 psi, they mark it for a 10. They say whenever the needle goes there, it's going to be 10 or whatever. This is a very simple, what they call an aneroid gauge for this. If there's low pressure out here, the opposite thing will happen. This bellows will expand outward, right? And then the needle will go down when there's low pressure. Very simple aneroid pressure gauge. Another way to measure pressure is to use what we call a manometer. If you take a piece of glass and you put a liquid in it, it can be water, it can be alcohol, it can be mercury. In fact, mercury is a really good one. And then you bend that piece of glass into a U shape, and you'll notice that when you have both sides open to the same atmosphere, then both liquids are at the same height. However, if you put a balloon on one side, put another bend in it and put a balloon on one side with high pressure air in it, then this is higher than the atmospheric pressure, and it's going to push on this liquid on this side more than the atmospheric pressure is going to push because it's higher pressure than the atmospheric pressure. So you're going to get this uneven liquid thing, and you have this height difference between the two sides. You plug that height difference into the equation for pressure and height of a fluid, and you'll be able to calculate the actual pressure. And you have to it's a good idea to put in the atmospheric pressure in there because you're talking about two pressures here. You have the absolute pressure and the atmospheric pressure. So here you can figure out the actual pressure inside the balloon. That's this pressure absolute. If you take the atmospheric pressure and add on the height difference times the density of this liquid right here times the gravitational pull. So this is a manometer, and you can do it the other way around too. So if you have something that's at a low pressure over here, then this side will be higher than this side. So low pressure, the atmosphere pushes the liquid further down than the side that has low pressure. Of course, there's no such thing as a perfect vacuum, really. There's no such thing as space that has absolutely nothing in it. So you always have a little bit of pressure, but it can be quite low. So a manometer is another type. Manometers are often used for blood pressure. And you can sometimes see it in your doctor's office. Sometimes you actually see the tube in it, and you'll see a liquid floating in it. And as they pump up the pressure, what they're doing is they've put a balloon around your arm. And then they fill that balloon with air. And as they fill that balloon with air, it cuts off your blood. And what they're doing with their stethoscope is they're listening when they release that air. They're listening for when the blood starts pumping again. So they listen to listen where it stops pumping. So they listen to see where it cuts off, and then they listen to see where it cuts back in. And that gives them their diastolic and their systolic. And then, they apply the pressure. So systolic pressure is measured by noting when the blood starts to begin to flow, and then diastolic pressure is measured when the blood flows without interruption. So when they're letting the air out, when they first start to hear blood flow again, then that's the systolic, and then when they completely let it out and your blood's flowing again, that's your diastolic, your lower. So the 120 millimeters and the 80 millimeters, that's kind of normal, 120 over 80. That's the systolic and diastolic pressures. And that's millimeters of mercury, because they use mercury in their manometers for that. So, how many of you have ever spent any time in a doctor's office or a hospital where they take you up to an IV bag? Have you had an IV bag? You ever wonder why they put it at a certain height? So your blood has pressure in it. If that bag doesn't have enough pressure in it, in the fluid, then it won't get into your blood, because if the blood has a higher pressure than the pressure of the fluid in the bag, or the pressure of the fluid in the needle, then the blood will actually go up the needle. You ever seen that happen? And it doesn't feel very good. It's like somebody slowly drawing blood out of a big hole in your arm, because when they put that tube into you, it's usually a tube, not a needle. They use a needle put in, but it's a pretty big tube when they put those IV bags in. So, so what they do is they put that in, and they put it at kind of a common height for most people. Most people's blood pressure is about the same. But if they see blood in this tube down here, then they raise it up, and they get that pressure higher. And because the height, of course, determines the pressure. The height above the arm, it's kind of like having a dam. With a higher dam has higher pressure at the bottom, and a lower dam at the bottom, right? So it's like making the dam higher by lifting the bag up higher. And then if it's going in too quickly, if the flow rate is too high, then they lower it down. Nowadays, what they do is they actually put a little device in the tube that's a flow rate meter that they can actually measure the rate of the flow, and then it can actually adjust it. And then they just put the bag up high and not worry about it. But in the old days, they had to adjust it constantly, make sure it was correct. So 0.24 meters above the entry point, and for the fluid to enter the arm at a very, very slow rate. And usually they'll put about a half a meter up, just to not be a problem. Here's another device for measuring pressure, the barometer, right? So you take a long tube of glass, then you seal it up on one end. Then you fill it with a liquid. And then without letting any water out of the tube, so you fill it all the way up to the top, so there's even liquid coming up over the top. You know how you get that little meniscus on the top? And then without letting any liquid out of the top, you turn it over into a tub of the same liquid. And what you'll see is you'll see a little gap form at the top here. Now, if this is water, the gap will be huge, unless your tube is really long. If your tube is really long, well, no, let's see, the gap will be bigger. Actually, no, your gap will be small if it's water, if I'm remembering correctly. Yeah, your gap will be small if it's water, unless your tube is super long, like meters long for water. But if you have mercury in there, a very, very dense liquid, then you'll get a pretty big gap here. And it doesn't even have to be that long, like a little bit more than a meter, or a little bit less than a meter, about a meter long. You get a pretty big gap in there because mercury has a lot of mass per unit volume, a lot of density, so it really wants to fall out of the tube. But this vacuum up here has nothing in it. What's happened is that the liquid has fallen out of the tube a little bit, but because it's sealed up down here, it can't fall all the way out. Because this vacuum up here, it's kind of like it's holding it in, sucking it in, if you think of it as. But that's not really what's happening. What's really happening is that in this tub of mercury out here, you have the pressure you have the atmospheric pressure pushing down on that tub of mercury. And the atmospheric pressure is enough to hold up this much mass in the tube. And in most places on the Earth's surface, that's about 750 millimeters of mercury, or about 29 inches of mercury. So that's what they mean when they tell us that we have 29 inches of pressure. It's 29 inches of mercury in the barometer. So again, this is actually measuring the pressure of the atmosphere. In the atmosphere. Here they do a bunch of conversions from atmosphere to Pascal. So 1 atmosphere is about 100,000 newtons per meter squared, or 100,000 newtons. But they also have some other conversions. We have dynes per centimeters cubed, pounds per inch squared, millimeters of mercury, all these other ones. So it's kind of 1 atmosphere is 760 millimeters of mercury. Millibars, lots of pressure units. Now we move on to Archimedes. How many of you have heard of Archimedes before? Nobody? Yeah. Do you know what he's famous for? What's that? Yeah. So Archimedes, he lived back during the empire, the Greek Empire. There's a couple of pictures I'm very fond of when it comes to Archimedes. This is a great one. Archimedes was the one that said, give me a lever long enough and I'll move the world, right? So Archimedes did a lot of stuff with machines. Archimedes moving the world there. Archimedes also was the one who did the experiment with putting objects in water to see how they displaced the water. And this is actually what he's most famous for. The king of Syracuse, which is where Archimedes was from. So we got to show this picture because that's great. So Archimedes the king gave Archimedes his crown and said, I'm afraid that my goldsmith has cheated me. He gave some pure gold to his goldsmith and said, make me a crown. And when he got the gold back, he suspected that the goldsmith had mixed some of the gold with some copper or some silver. And if you do that, it's very difficult to tell in any way. It still looks like gold, but of course it's just not pure gold anymore. And so he wanted to know if his goldsmith had cheated him. And he gave Archimedes the task of figuring this out. And as Archimedes was taking his bath one day, he noticed that when he brought his arms into the bathtub, 2 things happened. First of all, as he brought them into the water, what happens to the level of the water? It goes up. And as you push your arms into the water, what do you feel? Is it easy to do that necessarily? You kind of have to force them under the water, right? You kind of have to force them down, and the further you go down, the more you have to force. You have to push down. So he figured out 2 things from this. First of all, that the objects that are put in water are displacing the water. Where does that water go? Well, of course, it goes up because the water level goes up. And that raised water level is creating a force upward on the object in the water. So as you're trying to push it down, the water's trying to push it up. That's the resistance you feel. And that force comes from the displaced water. The displaced water has been risen higher up in the tub, and it wants to get back down to where it was. So it's pushing down on the water below it, creating more pressure. And that pressure is pushing up on your arms. And he said, well, I can make use of this. So he jumped out of his bathtub and went running through the streets of Syracuse, yelling, Eureka, which means, I have found it. And of course he was naked because he was in his bathtub and his grease and nobody cared about being naked. But it's a funny story. He also invented the first water pump. This uses a screw. You turn this up here and the water gets scooped up into this screw and gets carried from a lower to a higher place. So he did a lot of things with liquids. kind of funny. Statue of Archimedes. Let's see what else did he do that we can. He did a lot of things with geometry. A lot of cool stuff with geometry. And let's see, what else? He did a lot of things with trigonometry as well. Oh, here's one of my favorites. I just saw it. He did some things with light. He made parabolic mirrors. I just saw it. Oh, here you go. He made these parabolic mirrors where he could capture the light of the sun or the light of, the light of the sun. He captured the light of the sun and reflected down to ships that were coming in, because Syracuse was on a peninsula and people who were conquering it always wanted to conquer it with ships. But he would reflect this light down onto ships and catch them on fire. He would catch their sails on fire, and of course cause them much trouble. This is another classic. There's a better picture of it here somewhere. Here's another classic. When Archimedes, when Syracuse finally was overrun, and it was once, eventually it was overrun by people. The Romans who were conquering Syracuse at the time, their leader insisted that nobody harm Archimedes. He wanted Archimedes to be spared so that he could meet him and speak with him and learn from him and help him continue his work. Archimedes wasn't even paying attention when Syracuse was being attacked, and he was working on some project in some mathematics, and he was drawing in the sand on the floor of his home, doing some geometry or whatever, some figures or math or whatever he was doing, and this soldier came in and put a shadow over his work. And Archimedes said something like, "Who's the idiot, making it difficult for me to work, or something, blocking my light," or something like that. And the soldier was so insulted that he killed him right then and there. And I'm sure the soldier died as a result of killing Archimedes. But anyway, Archimedes was a brilliant man, a brilliant scientist, brilliant philosopher in many, many ways, and contributed a lot to the technology of the world. So, anyway, that's Archimedes. The Archimedes principle we're going to talk about is this principle that he discovered when he was doing the project for the king with the crown, and that is this idea that when you immerse something in water, there's a force that pushes upward on it. And it doesn't even matter if the thing floats or sinks. Have you ever tried to throw something heavy into a pool and notice that it doesn't fall to the pool as quickly as it would fall to the earth in the air, right? So, and this is due to, in part, the Archimedes principle. This idea of displaced fluid creates this upward force. And this upward force that the displaced fluid creates is called the buoyant force. That's the force that is the upward force on an object that's in a fluid. And it doesn't matter if the fluid's a liquid, it happens in air as well. So hot air balloons, for example, float because of Archimedes' principle. They float because they're this big object and they displace more air. The mass of air that a hot air balloon displaces is actually bigger, or the weight of the air is bigger than the weight of the balloon. And that's the idea. So here is the basic Archimedes principle right here. The buoyant force on an object that is in a fluid is equal to the weight of the fluid that it displaces. So if you're in water and if you displace 1,000 pounds of water, then you'll have 1,000 pounds of force pushing up on you while you're in that water, displacing that fluid. Right? Now, what if you have a block of metal? Let's say you have a block of metal inside of water. That block of solid metal is going to sink. It's not going to sink as fast because the buoyant force is going to push up on it. But how much is the buoyant force going to push? Well, it's going to be equal to the weight of the fluid, the weight of the water that would have been in the place of that block if the block wasn't there. So if it's 10 pounds of water that it displaces, so a gallon, let's say we have a gallon of water that we displace by putting we take a milk jug and fill it with aluminum powder or steel powder or something like that. And we displace a gallon's worth of water with a gallon's worth of steel, right? That gallon worth of steel is going to feel 10 pounds approximately, because a gallon of water weighs about 10 pounds. It's going to feel about 10 pounds of force upward on it as it sinks to the bottom when we let it go in the water. That's not a lot of force on a gallon of iron, but it's some, so it'll slow the iron down a little bit, and the iron will slowly fall to the bottom, slower than it would in air. And in fact, even if you drop that gallon of iron filings in air, it drops slower than it would in vacuum because the air has a buoyant force on it. Now, 1 gallon of air doesn't have much weight, so it's not very much buoyant force on it. However, if you take 1 gallon of air and displace it with 1 gallon of helium, that is enough to make it float. So 1 gallon of helium is an average sized kid's balloon, right? The balloon itself has very little weight to it, just a tiny bit of weight. But if you fill it with a gallon of helium, that gallon of helium is going to fill that balloon, that space, it's going to fill up a gallon of a big space of air that is actually going to have more weight. The weight of the air that is displaced weighs more than the balloon and the helium inside the balloon, if you can believe that. The weight of the air that is displaced by a balloon weighs more than the balloon and the helium that's in that balloon. And that's why it floats. Because the buoyant force, if the buoyant force is equal to the weight of the air displaced, and that's bigger than the weight of the object that's now in that place, then the force upward will be more than the force downward, and it will float. And that's the idea of Archimedes' principle. So here's an example. We take 10,000 metric tons of solid steel, and we dump it in the water in a big block. It's going to sink. It's not going to sink as fast as it would in air because of the buoyant force, right? So what's the buoyant force on that much steel? 1.28 times 10 to the 3 meters cubed is how much area or how much volume that steel is going to take up. And the mass is equal to the density times the volume, so we calculate the volume. And then Archimedes' principle says we'll have 1.3 times 10, 7 newtons of force upward, but the weight downward is so much bigger. It's 9.8 times 10 to the 7. So you have 9.8 is the weight down, 1.3 is the force, the buoyant force up. It's going to fall. Weight is much bigger than the buoyant force. However, if we take this steel and we stretch it out into a great big boat, so we roll the steel out into sheets, and then we weld it into a big boat-shaped thing, and then we put it into the water, how much water is it going to displace? It's going to be the same weight, it's the same amount of steel, the same weight, but it's pushing more water out of the way because what's inside of the boat? Air is inside the boat. In other words, the boat is no longer solid steel, it's hollow steel. And all that air has very little weight to it compared to steel. But the steel is moving a lot of water because we've spread it out over this huge area. So it's spreading it out over the water. It's moving much more fluid, much more water. And we get, instead of 1.28 times 10 to the 3 meters cubed of displaced water, we get 1 times 10 to the 5th meters cubed of displaced water. 100 times more displacement. We've moved a lot more water. That means the buoyant force is going to be much bigger, 9.8 times 10 to the 8 newtons. And guess what? 9.8 times 10 to the 7 was the weight of the steel. So the steel is being pulled down by gravity with 9.8 times 10 to the 7 newtons. But the buoyant force is pushing up with 10 times more force. This boat is going to float. And it will have room. You'll be able to put stuff in it. It's got 10 times more buoyant force than it does weight force. It's floating on the top. You can put more in it until it's not quite floating on the top. So that's Archimedes' principle. Now, if you combine the idea of density with Archimedes' principle, you get this idea right here. The fraction of an object that is submerged is equal to the volume that is submerged over the total volume of the object, which is also equal to the volume of the fluid displaced over the volume of the object. Or the fraction of it submerged is equal to the average density of the object divided by the average density of the fluid. Either one of these equations can be very useful, and even this middle one that has the mass and the density in it. But what that results in is you have a boat that doesn't have very much stuff in it, doesn't have very much mass inside of it, when it's going out to sea or coming in from sea or whatever. You can see that it's not very deep in the water. But the more stuff that it has in it, the deeper it gets into the water. And that's actually why they paint this stripe on the boat. You ever wondered why cargo ships have a stripe painted on them? That's why. They can actually tell how heavily loaded a boat is just by looking at that stripe on the boat. So right here you can see this one's not very heavily loaded. Looks like it's got a lot of stuff on it, but it's not very heavily loaded. This stuff must be pretty lightweight stuff. That's all there is to it. This one, much more heavily loaded. See, that stripe is almost to the sea line. And that is essentially that's the limit for this ship. It's not supposed to be loaded more than that. This one is loaded. Holy crap. All the way down to the line, essentially. Can't even see the line there, right? And every ship is a little bit different. You can see this one, the keel is almost out of the water. It doesn't have hardly anything on it at all. And this one, it's not loaded at all anymore. It's unloaded into the sea. Capsized. But here's one that's not very well loaded. How'd you like to be this one is a Nissan cargo ship. All the cargo is, of course, driven off. It's just cars. Can you imagine driving the cars off? It's like 5,000 ships. Oh yeah, or 5,000 cars you have to drive off the ship. Sorry. The biggest parking garage, floating parking garage ever. Anyway. Okay. Archimedes' principle. Here's another definition. We call this the specific gravity. If you take the density of an object and divide it by the density of water, you get the specific gravity of that object in water, which tells you essentially if it's going to float or sink and how much it's going to float or sink. If you have a specific gravity, if your specific gravity is much less than 1, it's going to float. If it's close to 1, it's going to be neutral in water. So if it's really close to 1, it might float below the surface. It might sink really, really slowly. It might float just barely on the surface, but it's going to be pretty neutral. And then if you have a specific gravity that's greater than 1, the higher above 1 it goes, the more quickly you will sink. So that's specific gravity. Here you have a person that's 60 kilograms. They float in fresh water with 97% of the volume submerged. So the fraction submerged equation right here, you can use densities, you can use volumes, either way. In this case, they're using densities, and they're going to calculate the average density of the person. In fresh water, you would use 1 for the density of the fluid. Salt water actually has a higher density. So people float higher in salt water. And oftentimes, salt water is where world records are formed for swimming, right? because if you're floating higher in water, you have less resistance, you swim better. So they actually had to start making a conversion. If you're swimming in a saltwater pool, then you have to convert your times up and change your world record times. But here they take, they're calculating, they want to calculate the density of the person, which is the object. So they solve this equation. The fraction submerged is the 97% as a, take 0.97 instead of 97. And then that's 0.97 times 10 to the 3 because that's the density of the person is going to be that. And then you get your sorry, it's the density of the water times the fraction. So you get 970 kilograms per meter cubed. And this is actually the only way to really measure the density of a human being very well. You may have had a density test done, a fat test, or a bone density test done. If you weren't submerged in water, it wasn't a very good test. Because the only real way you can do this is to take, you go in a tank, they call it a fat tank, it's not very flattering, but they put you in a tank and they measure how much of you, they measure the point at which you float, essentially. How much of you is submerged when you float. And the tank is designed to measure the amount of fluid displaced, essentially. And then from that they measure your density, and then they take some, they usually do a MRI or a X-ray, CAT scan of your body to measure your bone density, essentially. And then they use that together with the body density to measure your fat content in your body, your fat density. So they often have these in recuperative centers, hospitals, and also sports centers have these a lot. Well, here's an example of how you could measure the density of an object that is an unknown material. You measure the weight of it in air, or the mass of it in air, and then you measure its apparent weight when it's in a fluid like water. And then, after you're done with that, the apparent weight loss is going to be equal to the weight of the fluid displaced, and the apparent mass loss is going to be the mass of the fluid displaced, and from those two things you can actually get the density of the material. So here they do that. So here they calculate the volume of the water displaced by the coin, and then the mass of the coin itself from that, and then they take that mass divided by that volume, and they get the density of the coin at 10.4 grams per centimeter cubed. So it's pretty close to pure silver, and that's exactly how Archimedes measured the crown of the king of Syracuse. Now I can't remember if the crown was pure gold or not. So I can't remember if the goldsmith lost his head or not. But, and that's Archimedes. Now these last two sections, I don't think I've given any homework on surface tension and capillary action, but they are related to these things. But they're more about internal forces in between the molecules rather than actual pressures. So it's called cohesive and adhesive forces. Cohesive forces are the forces that keep liquids together. That's what makes them stick to themselves. And adhesive forces are the forces that make them stick to other things. And some liquids have very, very high cohesive and adhesive forces, like soap bubbles. Soap bubbles are made of long chains of polymers, and polymers are very, very sticky to each other. That's what plastics are made of as well. And so you can make great bubbles out of them and other things. You get this surface tension effect with liquids where, there are certain animal or insects and things that can walk on water. You can even make something like a very, very small needle float on water because of its surface area. And essentially what that comes down to is something with a fairly large surface area but a very low mass, very low weight, can take advantage of these forces that are in between the molecules that hold the water together, and they can essentially float on water without having to actually float according to Archimedes' principle. And they have some equations for these, but like I said, I don't think they give any rules. And then of course the cohesive forces can also, you can also create these thin films, they call them, and bubbles or whatever. And they talk about the surface tension in these waters and everything else. This is also responsible for a lot of the things that go on inside the body, since water is an important thing in the body and there's lots of stuff in there. It's also important for functions of soap, and I mean there's lots of different things that take advantage of this. But I'm not going to go into great detail on all this stuff, so we'll move on with that. At least I don't think I do. Pretty sure I don't. We don't mess with it. Okay, so anyway, and then this last one, they talk about some of the pressures in the body. So the pressure in the body, systolic, diastolic. That's for kind of an average normal person. If you're outside this range, you starting to be unhealthy. You could be in danger of having a stroke. Essentially, if your pressure goes too high, what happens is when your blood pressure is too high, your blood flow is going down. So you essentially have something blocking the flow. Usually, when your blood pressure is too high. So they look for that first. They look for your fat content. They ask you what your diet is. Make sure that you don't have any problems with that. But blood pressure can also just be caused by stress. Stressful situations in your life can cause high blood pressure. But high blood pressure usually comes from slower moving blood. And when blood is moving more slowly, then you don't get blood flow to the brain, and you can get a stroke. Essentially, that's what essentially happens. When blood doesn't flow to the brain, part of your brain can start to die. And if your brain starts to die, you get nerve problems, your face starts to droop, you get slurred speech, all these things, you get a stroke. And then if that happens, if that is extreme, it can become permanent, semi-permanent, or very permanent. So people who've had strokes often have problems with motor function, with speaking, seeing, nerve things in their face, especially. Entire half of your body can go dead. Your whole body can go dead. So it's essentially a blood into the brain thing is what a stroke is. But another thing that can happen is if your blood pressure is too high in one place, it can actually make it very low in another place. So for example, if you have stuff in your veins from eating too much bacon, that's probably the most common thing in the world. It's the most common thing in the United States for causing stroke. People eat too much bacon. Bacon is by far the most unhealthy thing in the world to eat, because the fat from bacon literally goes into your veins and arteries and plugs them up. And when it plugs them up, it creates a very, very tiny hole for the blood to go through. And the blood has to go super fast through that hole to get through. But it creates a backup behind it where the blood goes super slow. So where it's going slow, you have a super high pressure region. Where it's going fast, you have a super low pressure region. And that low pressure region has pressure outside the vein pushing it in. And if it gets super, super low going through the tight region where there's that clot of blood, that clot of fat rather, blocking the blood, then the pressure outside will squeeze it even tighter, and it goes even lower in there, and then it squeezes even tighter, and it can actually collapse the vein, and that can create a stroke again. That can create another kind of stroke. So, and those are the worst kind, because that's not a slowing down of blood, that's a stoppage of blood. And when that happens, you're in serious trouble. That can cause a stroke, and it can cause a heart attack as well, because of the stroke. Because if that cuts off the blood to your heart, for example, or the blood, it can cause all kinds of problems. So the moral of the story is take it easy on the bacon. Bacon is not good for you. So, So when somebody goes into shock, their blood pressure goes down. Right? Their blood pressure goes way down when they go into shock. So what do you do when someone's in shock? What do you do with their feet? Raise them up. Someone's in shock, you put them on the floor, and you raise their feet up. And the blood flows up towards the top of their body, gets into their heart so it can start pumping it again. But it keeps the blood from going to the feet. If you get that blood up to the top of the body where the brain is and the heart is, you're in a much better place. I mean, where you want that blood pressure to come up is in the brain and the heart area, so you can get things going. So that's not a pleasant feeling. The blood pressure bottoming out is kind of weird. I've had that happen to me before. It wasn't because of shock, it was because of the medication I was doing. Pressure in the eye. So your eye has all kinds of veins and arteries in it. Because your eye is clear, it has to be clear so that light can go through it and you can see. Your optometrist can look into your eye and actually look for signs of high blood pressure and other problems with blood pressure. If you have a high blood pressure, the blood starts pushing into places in the eye that it shouldn't be. It creates a weird effect in your eye, and that's how they can tell if you've got extreme blood pressure that needs to be worked on. But it can also, at high pressures, it can cause real problems. Start bursting blood vessels in the eye, start breaking things. It can actually separate things in the eye, and it can actually cause blindness eventually. So you've probably heard of glaucoma. That's one of the conditions that can cause a high blood pressure in your eye, and lots of other things. Pressure in the lungs. So I've had this. So between your lungs and your chest cavity is a vacuum. And the pressure, the air pressure outside is what keeps your lungs stuck to your chest cavity, essentially. You have the air pressure in your lungs pushing them against the air cavity, and there's no way for air to get in between your chest and your lung. Naturally, well, normally there's no way to get in there. But if you get a punctured lung, then air can escape from your lung into the chest cavity. And then you have air pressure between your ribs and your lung. And that will actually cause your lungs to collapse. And that hurts. I've been told it's like a heart attack, but I've never had a heart attack, but I have had a lung collapse. And with mine, my lungs are just, for some reason when I was young and growing, my lungs grew way too fast and were too big. So my lungs are about 30% bigger than they should be. And that created some stretchy, weak spots in my lungs. And one of those weak spots just tore open one day. And it felt really terrible, and it got worse and worse. But my left side lung essentially collapsed down to about 20% of the size. And it just pulled away from the chest cavity. And as it pulled away from the chest cavity, it ripped a bunch of connective tissue off of my ribs and my lung, and my heart. So that's what caused, and I had like the sharp pain down my left arm and all this, craziness. And because it's the same nerves essentially that it pulls on. But how do you fix something like that? Well, you have air between your lung and your chest. You have to get that air out. So one way to do that is to just cough a lot. If you cough, when you're coughing, what you're doing is you're forcing air out of your lung into your body, into the air around you in a very forceful way. But if you've collapsed 80% of your lung, that's not going to be enough. So they actually had to put an ice pick in me. They punctured my chest right about here and put a hole in my chest, and then they stuck a tube in there, and then they sucked the air out with a vacuum for a day. They just sucked the air out of my lung, so that my lung, out of my chest, so that my lung could reinflate itself as I was breathing. So I had to cough constantly for like a day as they were sucking air out of my chest. And then when they sucked all the air out of my chest, they put a one-way valve in my chest that would just let air out and wouldn't let any air in. So for the next week or so, every time I cough, this little thing would go psst, get a little air out of my chest. Psst, psst. A little blood sometimes too. But it was kind of interesting. Pressures, lots of pressures. And that pretty much does it. We're done today. Right on time. So go ahead and get started on the homework. It's not terribly challenging homework. There's nothing really there that we didn't see an example of here. There's no force diagrams or craziness like that. Um, just try to get all of it done that you can. We'll answer any questions you have for a few minutes tomorrow. If you have a lot of questions, try to get in a little early and talk with the TA so that we can use as much class time as we can for chapter 12. And then we'll hit chapter 12 tomorrow as well, which is kind of more of the same except with moving fluids. It's a little more complicated, but we'll get as much done as we can with chapter 12. We might have to finish up chapter 12 on Wednesday before we start the lab, and then we'll do a lab on Wednesday. Sound good? All right. Have a good day.